Hi there, my name is Aaron Lanterman. I'm a professor of electrical engineering at Georgia Tech, and I would like to welcome you to the 10th lecture in the summer 2020 offering of ECE3084 Signals and Systems at Georgia Tech. Today we'll be looking at convolution. This is probably the most complicated subject we'll look at in the class, so it's good that we're taking care of it early. So in the last lecture, we looked at linear and time-invariant systems and created a notation that said that we could find the output of a linear time-invariant system by integrating the input x of tau here against the impulse response, here labeled h of t minus tau, integrate over tau, and we would write this as xt, this asterisk symbol, times h of t. Now, I'm not personally a big fan of this notation. It makes it look like you should plug in 42 for t, figure out what that is on x of 42, figure out what h of 42 is, and then do a couple things with those numbers. But really, convolution is something that applies to entire functions and gives you an entire function out. And this kind of notation would emphasize that. However, the ECE 2026 textbook uses the notation in the first line and not the second line, as well as some other textbooks. So I'm going to go ahead and go with the notation used by the 2026 text. We can do a change of variable and rewrite this integration by swapping the role of h and x. So we could write h of tau, x of t minus tau, d tau. And this essentially tells us that convolution is a commutative operation. I can change the order around the asterisks. I really wish that the people who created the notation of convolution would have picked something other than an asterisk, given that an asterisk is used to represent multiplication in most programming languages, and we also will use an asterisk to represent a complex conjugate operation if we use the asterisk in a superscript kind of mode. We're looking at convolution from a signals and systems context where x and I represent inputs and outputs and h represents a impulse response. But convolution is a general mathematical operation and shows up in other contexts such as probability theory. So the things that just have tau in them are going to be called the fixed functions when we try to figure out how to actually graph out doing this convolution. Here are the things that have the t minus tau. We'll think of those as the functions that we're flipping and shifting. We should be able to do any given convolution problem either way and ultimately get the same answer, even if the steps we take to get there are different. I will sometimes call the flipped and shifted function the slidey block. That is a Aaron Lanterman specific term that you are unlikely to hear other instructors using. So we'll need a couple of functions for our demo. For x of t, let's have a function that goes from 1 to 2, goes from the values of 1 to 2 at the time values of 1 to 2. You shouldn't read anything interesting into the fact that I have a value of 2 at time 2. It's just a quick, easy function to write and draw. And for h of t, let's use a decaying exponential function that starts at 3 and that ends at 6. I'm not going to try drawing this to any sort of sensible scale. This certainly will start at 1, at 3. So I'll write, let's say this is e to the minus 4 t minus 3, u of t minus 3. So it's a decaying exponential that shifted over by 3. So it starts at 3. And I put a decay factor of 4 in here. Now, I'm not trying to draw this accurately. All we really need from this is that we have a sense of the support of the function in time left to right along the horizontal axis. If I try to make a realistic drawing of this, it would actually decay much, much faster. We need to pick one of the functions to be fixed and the other function to be flipped and shifted. When I teach this class in person, I'll often ask a student in the class, what's the most you've ever lost in a coin toss? And depending on their reaction, I can figure out if they've seen No Country for Old Men or not. If you haven't seen No Country for Old Men, it's a very lighthearted kind of romantic comedy. It's starring Adam Sandler. Okay, no, it's not. It's an intense and violent but brilliant movie by the Coen brothers. So I'm going to do a virtual coin toss, and by that I mean I'm not going to toss a coin at all. I'm going to pick which one I want to have fixed, and I'm going to pick which one I want to shift. Oops, sorry, I forgot. I need a u of t minus 6 here. Need to subtract that to make this function actually shut off at 6. So I'm going to pick x of t to be the function that I flip and shift, and h of t to be the function that we keep fixed. So we're going to be using this version of the convolution formula. So I'm going to plug tau in for h and t minus tau in for t. Remember the t in the x of t definition and the t in the t minus tau. You should think of those as being different t's. So I'll draw an axis, and on this axis I'll draw h of t, but I'm really drawing h of tau. This is a tau axis. And what we're going to do is essentially integrate over tau, integrate over this graph, in order to figure out what y of t is for some particular t. X of t is going to be what I flip and shift. It's probably easiest to manipulate this expression and write it as x of minus tau minus t. So now we see that the minus sign at the beginning of that argument provides a mirroring operation. And then in terms of making a plot versus tau, that minus t results in my x function that I'm representing in blue here being shifted to the right. And plugging in different values of t to shift by the right by different amounts t will give me sort of different integrands that when I perform the integration give me the different values of y of t. So to get our minds thinking about convolution, I'm first going to write x of t minus tau on this graph in blue here for the particular value of t equals 0. In general, this mirrored function will have a left edge at t minus 2 and a right edge at t minus 1. Of course, for the t equals 0 point, just to get our brains going, these edges will be at minus 2 and minus 1. As we increase t, this blue function I've written here, this x function, is going to move to the right. If I decrease t, then the function is going to move to the left. When I analyze the convolution, I'll have 5 different cases here. The case shown on this graph represents no overlap on the left. So we have the function that's sliding to the left of the purple block, and there's a large range, like where I've drawn and dotted here, that you could set t at to move this block to. And what happens in this case is that all of the places where the function is purple, when you pointwise multiply it with the blue function, well, the blue function is 0 in that region. And all of the places where you have the blue function, well, the purple function is 0 in that region. So when you do that pointwise multiply, the entire function is 0. So when does this no overlap on the left case take place? It's when the right edge of the blue block, the slidey block, which is at t minus 1, is less than, i.e. to the left of the left edge of the stationary block, the purple block, which is at 3. And if I solve this out, I get t less than 4. So we have a similar situation when there's no overlap on the right. Here, again, any of the parts of the purple block are going to be zeroed out by the places where the blue block is 0, and any places where the blue block isn't 0 are being zeroed out by the place where the purple block is 0. Once again, we have a case where the edges of the moving block are at t minus 2 and t minus 1. So this case happens when the left edge of the blue block at t minus 2 is greater than, i.e. to the right of the right edge of the purple block. And if I solve that out, I wind up with t greater than 8. One thing I want to emphasize when I talk about overlap is that I'm referring to overlap in the left and right tau axis. I'm not talking about some sort of two-dimensional set intersection that students will sometimes interpret the term overlap as. It's overlap in terms of the support in the time domain. So let's go back and take a look at the integral that we're actually doing. And I mentioned earlier we're going to have 5 different cases. So I'm going to write this giant case statement like in a computer programming language. In each of these, we're going to have an integral. So I'm going to write 3 integrals for the middle, and then I'm going to write 0 for the edge points because I know the result of those integrals is going to be 0. Those are the 2 cases we've already looked at of partial overlapping on the left and partial overlapping on the right. And when I write the functions I'm integrating, I'm going to just write the main core of the function, for instance, the t, but without the u's, because we're going to take the effect of the u's and include them in the limits of the integrals. So we're going to plug in t minus tau for t. So we're going to write this as t minus tau, t minus tau, t minus tau. So that's plugging in t minus tau for t. Notice I haven't included the unit step functions because we're going to encapsulate their effects in the limits of the integrals. So that's something we'll need to figure out later. In the meantime, let's go take a look at the function that we kept fixed, namely h, which is the decaying exponential function. For that, we're just going to plug in tau for t. Once again, we're not going to put in the step function. So I'll write e to the minus 4 tau minus 3, e to the minus 4 tau minus 3, e to the minus 4 tau minus 3. So the integrals on all of these are the same, including the ones at the ends, at the top and the bottom here. I just know ahead of time that those are going to give me 0 because those are the non-overlapping cases that we've already looked at. And what are those cases that give me 0 out? Well, I have t less than 4 for the first case and t greater than 8 for the last case. So I can go write those into my big if-then statement. And then we're left with 3 others to figure out. So I made a few more of these axes where I put down the purple block, the h of tau block, aka the fixed block. Now imagine we took our blue block, the x of t minus tau block, and we increased t to move it towards the right. Eventually it's going to hit the purple block, and it's going to get to a point where the right edge of the blue block is matching up with the left edge of the purple block. At that point, we have what we'll start to call partial overlap on the left. And we'll have that for a bit as the time increases and the blue block moves forward. Eventually, we'll hit a point where the left edge of the blue block matches the left edge of the purple block, and when it keeps moving right, we'll then enter what we'll call a total overlap stage. So in general, we'll actually have something in between these 2 points, and let me illustrate that by drawing it, say, going from 2.5 up to 3.5. Oh, I should notice I don't really actually have these 2 vertical scale very well. The blue block goes from 2 down to 1, and the decaying exponential actually starts at 1 and then decays. I think that's okay here because we're really only needing these graphs to figure out what the quote-unquote overlap is in the horizontal dimension and the tau dimension. Where does partial overlap on the left take place? So we'll say that the left edge of the purple block, which is at 3, is bracketed by the left edge of the blue block, which is at t minus 2, and the right edge, which is at t minus 1. And it can sort of slide back and forth in that range. And so we'll say that 3 is between t minus 2 and t minus 1. If I solve for t in these 2 cases, then I wind up with t is less than 5 and t is greater than 4. In other words, t is between 4 and 5. So this is this partial overlap on the left stage. I can go up to our big case statement and now write in 4 and 5. Let's take a look at the other side. Let's talk about partial overlap on the right. As it slides forward, we'll eventually get an overlap in the middle, but let's skip that part for now, the total overlap case. Let's go to partial overlap for the right. Eventually, the right edge of the blue block will match up with the right edge of the purple block, and as we increase t further, we'll then get this partial overlap on the right case as we leave the total overlap case we'll look at later. So again, the blue block goes from t minus 2 to t minus 1, and so the overlap stage in this case is going to be where the right edge of the purple block at 6 is bracketed by the edges of the blue block, which are at t minus 2 and t minus 1. If I solve for t, I can wind up writing t less than 8 and t greater than 7. So this partial overlap on the right case corresponds to t between 7 and 8. And we can go back up and put that into our case statement, 7 and 8. Okay, so let's look at the final, most complicated case where we have the total overlap in the middle. So here the blue block support and the time dimension is entirely encapsulated by the support of the purple block, the fixed block in the time dimension. So here the left edge of the blue block, which is at t minus 2, is greater than the left edge of the purple block, i.e. to the right of that left edge of the purple block at t equals 3. And I could solve that to get t is bigger than 5. The right edge of the blue block, which is at t minus 1, is to the left of, i.e. less than, the right edge of the purple block, which is at 6. And if I solve that, I get t less than 7. And if I put those both together, I can write that this case of total overlap has t between 5 and 7. So for this middle case, I'll write 5 and 7. Now, a quick check is that all of these things need to match up. So the 4 here needs to match the 4 here. The 5 here needs to match the 5 here. The 7 here needs to match the 7 here, or whatever these numbers are. We have to cover all the cases. The 8s here need to match also. You really don't need to actually reason through the cases of all of these because we know that eventually they're going to have to match. The easiest ones to figure out are always the ones on the edge. So my recommendation is to figure out, say here, the t minus 4, t bigger than 8, the edge cases. And I used to recommend figuring out the middle case first because then you get the other two cases and you're only thinking about one more case. But the middle case tends to be more complicated. And so nowadays, what I usually recommend is to reason through the partially overlapping cases on the left and the right, and then use that information to fill in the middle case. Of course, it's not a bad idea to separately try to reason through the middle case to see if what you have makes sense. So we figured out how to figure out the edges of the if-then case statement here, and now we need to focus on figuring out the limits of the integrals. Remember that we left the u's out of the expressions we put into the integrals because we would take the effect of the u's and incorporate them into the limits. Oh, I just noticed that I swapped the order in which I wrote x of t minus tau and h of tau in the expression. I think I did that just because I'm used to seeing linear factors going in front of exponential factors. Let's start by looking at the partial overlap on the left case. Whatever interesting things might be happening in the left edge of the blue block are getting cut off by the left edge of the purple block. Similarly, anything interesting happening in the right part of the purple block is getting cut off by the right edge of the blue block. So the only place where anything interesting is happening is between 3, which is the left edge of the purple block, and t minus 1, which is the right edge of the blue block. Now, the left edge of our integral then is going to stay fixed, and then the right edge, t minus 1, can slide around with t. The function that we're going to integrate is a pointwise product across tau. With the way I'm drawing this, I don't want you to think it's like a 2D intersection. I'm just indicating that we're going to integrate over tau. I'm not going to try to plot exactly what the product of these two functions is, because I'm not sure I could freehand that accurately. But it doesn't really matter, since all we need here is to figure out the limits of the integration. So our limits for this case go from 3 in the lower limit up to t minus 1 in the upper limit. So next, let's look at the partially overlapping case on the right. The way I drew this isn't quite clear, so why don't we make a slight modification and pick a t that moves us a little bit more to the right so we can get a clear sense of this partial overlapping case. So I'll draw this from 5.5 to 6.5, and I should probably redraw the arrow for the t minus 1. So in this case, anything interesting that is happening on the right side of the shifting blue block is going to be cut off by the right edge of the purple block. And anything interesting that is happening in the left part of the purple block is going to be cut off by the left edge of the blue block. So the integral is going to go from t minus 2 to 6. So the integral is going to have an upper limit of 6 and a lower limit of t minus 2. So now let's look at the final and most complicated case of complete overlap. Here, the block that we are sliding is shorter in time extent than the block we kept fixed. So we're going to have the smaller block sliding within the larger block. If we had done the artificial coin toss the other direction, we would likely have the larger block sliding around the smaller block. So in this particular case, the larger block is staying fixed. And basically, anything interesting that is happening in the left or right of the purple block is getting cut off by the blue block. So the limits of our integral for this complete overlap case, this middle case, are going to go from t minus 2 to t minus 1. Now that we're able to fully fill in the limits of our integrals, we can notice certain patterns within the limits. For instance, the t minus 1 up here matches with the t minus 1 up here, and the t minus 2 down here matches with the t minus 2 down here. Notice that both of the limits of the middle case, the complete overlap case, are a function of time. If we had chosen to have our virtual coin toss go the other direction, and we had kept the shorter block stationary and chosen to flip and shift the larger block, then the limits of this middle case, this total overlap case, would be constants. Now, to figure out the various parts of the giant if-then case statement, you don't actually have to do all the work I showed you earlier. There's some tricks you can use. For instance, this lower limit of 4 of the start of the support of the answer, you can get from just adding the starting time of the x function and the starting time of the h function. So 1 plus 3, both those starting times equal 4, and that's the starting time of y of t. Similarly, you can get the ending time here, 8, by just taking the ending time of the x function and adding to it the ending time of the h function. 2 plus 6 equals 8, and that gives us our ending time of 8. We can also get the length of the answer by just adding up the lengths of the support of the functions that make up the convolution. So we can see that the answer has length 4, going from 4 to 8, and we can confirm that length by adding up the length of x, which is 1, and the length of h, which is 3, and 1 plus 3 is equal to 4. Although we've presented convolution here within the context of taking a signal x and getting the output y by convolving it with an impulse response h, remember convolution is a general mathematical operation useful in a wide variety of fields. So a question that always comes up is what happens exactly at these transition points? What happens at t equal 4, for instance, or t equal 5? Generally, the convolutions that you will see in real life and that I will give you in this class tend to have a smoothing effect on functions. Not always, but they often do. And the net effect of all of this is that the output is going to have a certain degree of continuity so that you can use either formula to figure out what's happening at the endpoints. So if you plug t equals 4 into this formula here, then you should wind up with 0 coming out. If you plug t equals 7 into this formula here, you should get 0 coming out. If you're looking at 5 here, you should be able to use either of these formulas. If you are looking at 7, you should be able to use either of these formulas and get the same answer. That's actually a good consistency check to make sure that things aren't going completely crazy. Now, another thing that you may have noted is I never actually got around to doing these integrals. And I didn't do that because I'm feeling lazy at the moment. These would be fairly complicated. You would need to do some integration by parts, and then you would need to substitute in the various limits. Luckily, you're only doing one indefinite integral and then putting in the limits. And the expressions you wind up with are often fairly difficult to simplify. And the fact that you could rewrite them in several different ways, but it's not always clear if one particular way is a more or less clearer answer or simpler answer than another one.